Hello there, and welcome back to Sleeping with Science Stories. If this is your first time on the channel, remember to subscribe and turn on notifications. And if this video brings you peace, leave a gentle like. Tonight, we will not stay on Earth. We will fly further out of the solar system, past distant galaxies, into the endless depths of the universe. And we begin our journey into the universe, where space is infinitely vast, where time flows slowly, where everything is calm and peaceful. How large is the universe? The answer is not simple. In fact, it is one of the most difficult, most wondrous answers that science can offer. Scientists estimate there are approximately 7.5 times 10 to the 18th power grains of sand on Earth. That is 7 quintillion grains of sand, a number difficult to imagine. But the number of stars in the observable universe is even greater than that, far greater. In the Milky Way, our galaxy, there are approximately 100 to 400 billion stars. Let us use 200 billion for easier calculation. But the Milky Way is only one galaxy, one among countless. And how many galaxies are there in the observable universe? Current estimates are approximately 2 trillion galaxies. Possibly more. New telescopes like the James Webb are discovering increasingly faint, distant galaxies. If each galaxy has an average of 100 billion stars, a conservative estimate, then the total number of stars in the observable universe is approximately 200 billion trillion, or 2 times 10 to the 23rd power stars. That is, compared to 7.5 times 10 to the 18th power grains of sand on Earth. So there are more stars in the universe than grains of sand on Earth. Approximately 26,000 times more. Let that sink in for a moment. Every grain of sand you hold in your hand represents 26,000 real stars out there, shining, living their own stories. And that is only the stars we can observe. The actual universe may be far larger, because there is a limit to what we can see. The universe has an age, approximately 8 billion years, and light travels at a finite speed, 300,000 kilometers per second. This means that light from distant objects takes time to reach us. Light from the sun takes 8 minutes. From the nearest star, Proxima Centauri, 4.2 years. From the Andromeda Galaxy, 2.5 million years. And from the most distant galaxies we can see, light has been traveling for nearly 13.8 billion years, almost the entire age of the universe. So there is a natural boundary to what we can observe, a cosmic horizon. Light from anything beyond that boundary has not had enough time to reach us since the Big Bang. It is still on its way, or it will never arrive due to the expansion of space. But here is the strange part. The distance to that boundary is not 13.8 billion light years. It is far greater. Why? Because space itself is expanding. While light is traveling toward us, the space between us and the light source is also expanding. So the object that emitted that light is now far further away than when the light began its journey. When scientists calculate, they estimate that the observable universe, the portion of the universe from which light can reach us, has a diameter of approximately 93 billion light years. Try to comprehend that number. 1 light year is the distance light travels in 1 year, approximately 9.5 trillion kilometers. 93 billion light years is approximately 880 billion trillion kilometers. That is the size of the observable universe, the portion we can, in principle, see. But the actual universe may be far larger, possibly infinitely larger, because our observational boundary is not the boundary of the universe. It is only the boundary of what we can see. Imagine you are standing in the middle of a vast plain at night. You have a flashlight. The light from the flashlight only reaches a certain distance. Beyond that, you cannot see anything. But that does not mean the plain ends there. It only means your light cannot reach further. Similarly, the cosmic horizon is not the edge of the universe. It is only the edge of what we can observe. Beyond that boundary, there may be more galaxies, possibly infinitely more galaxies. We do not know. And perhaps we will never know, because light from those galaxies will never reach us. But there are clues suggesting the universe is far larger than what we see. When scientists measure the curvature of space, by observing how light travels through the universe and how large structures are distributed, they find that space appears flat, or very nearly flat. In a flat universe, Euclidean geometry works. Parallel lines never meet. The sum of angles in a triangle is 180 degrees. And a flat universe, according to mathematical models, is typically infinite. Of course, space may be flat only within the portion we observe and curved at larger scales. But current measurements show remarkable flatness. If the universe is truly infinite, then everything that can happen does happen somewhere. Somewhere, infinitely far away, there may be an exact copy of you. Because in an infinite universe, every finite arrangement of particles will repeat. Somewhere, there may be another Earth identical to ours. Or slightly different. Perhaps you chose a different path in life. But this is speculation. We cannot observe those regions, so we cannot know for certain. What we know for certain is that the portion we can observe, the observable universe, is already vast enough to overwhelm our minds. 93 billion light-years wide, containing at least 2 trillion galaxies, each galaxy containing hundreds of billions of stars, and many of those stars have planets. The number of planets in the observable universe? Possibly trillions of trillions. And on some of those planets, there may be life. There may be civilizations. There may be creatures looking up at their sky and wondering, just as we do, whether they are alone. But the distances are too great. Even light, the fastest thing in the universe, takes millions or billions of years to cross the distances between galaxies. The nearest galaxy to us, Andromeda, is 2.5 million light-years away. If we sent a signal today, it would take 2.5 million years to arrive there, and 2.5 million years more to receive a response. 5 million years in total. Our civilization is only 10,000 years old. 5 million years is an unimaginable length of time, so we may never communicate with life in another galaxy. The distances are too great, the time too long. But we can observe, we can study, we can wonder. And in that wondering, we find a kind of peace, recognizing that we are part of something unimaginably vast. The universe does not revolve around us. Earth is just a small pale blue dot suspended in a vast darkness, as the astronomer Carl Sagan once said. But on that small dot, everyone we have ever known has lived. Every story has been told. Every empire has risen and fallen. Every moment of joy and sorrow, all on a small pebble floating in sunlight. And around us, in every direction, is space, vast, dark, filled with stars, galaxies, mysteries. 93 billion light years in every direction we can look, and possibly infinitely further than what we can see. The universe is vast. It is ancient. It is beautiful. And we, tiny creatures on a tiny planet, have the privilege of looking up and wondering about it. That is an unbelievably precious gift. The universe does not stand still. It is moving, changing, growing, and it is not only the objects within the universe that are moving. Space itself, the very fabric of reality, is expanding. Let that sink in for a moment. Space itself is expanding. This does not mean galaxies are flying through static space like bullets. Instead, the space between galaxies is increasing. Galaxies are being carried away by the flow of expanding space. Imagine a raisin bread rising in an oven. As the dough expands, the raisins, which were close together, move apart from each other. But the raisins are not moving through the dough. It is the dough itself that is expanding, carrying the raisins away from each other. The universe is like that. Galaxies are the raisins. Space is the dough. And the entire loaf is rising. How do we know this? In the 1920 Kaisudeki, the astronomer Edwin Hubble, after whom the famous space telescope is named, was studying distant galaxies. He noticed something strange. Light from most galaxies was shifted toward the red end of the spectrum, a phenomenon called redshift. Redshift occurs when a light source is moving away from you. It is like the Doppler effect with sound. An ambulance siren sounds higher as it approaches and lower as it moves away. With light, when a source moves away, the wavelength stretches, shifting toward the red, longer wavelengths. And Hubble discovered something even stranger. More distant galaxies had greater redshift, meaning they were moving away faster. What does this mean? If all galaxies are moving away from us and more distant galaxies are moving faster, then only one conclusion is logical. Space is expanding uniformly in every direction. And if space is expanding now, that means in the past, it was smaller. If you rewind time, galaxies were increasingly close together. Rewind far enough, and you arrive at a point when everything in the universe, all matter, all energy, all space, was compressed into an extremely small, extremely hot, extremely dense point. And from that point, the universe began to expand. This event, the birth moment of the universe, is called the Big Bang. But the name is misleading. It was not an explosion in the ordinary sense. An explosion occurs at a point in space and spreads outward. But the Big Bang did not occur at a point in space. It was the birth of space itself. Before the Big Bang, if before even has meaning, there was no space, no time, no where for an explosion to occur, no when for it to happen. The Big Bang was the moment when time and space began to exist. This is difficult to understand. Our minds did not evolve to comprehend such concepts. We are accustomed to the idea that everything has a cause, that time always flows, that space always exists. But physics tells us that time itself is a part of the universe, not separate from it. Time began together with space. So the question, what happened before the Big Bang, may have no meaning, like asking what is south of the South Pole. There is no south of the South Pole. It is the southernmost point. Similarly, the Big Bang may be the very first when. There is no before. Of course, this remains an open question in cosmology. Some theories propose that our Big Bang may be one of many, that there may be a multiverse with countless universes, each with its own Big Bang. But this is speculation. We cannot observe beyond our own universe. What we know for certain is that the universe had a beginning approximately 13.8 billion years ago, and since then, it has been expanding and cooling. But that expansion has not always been uniform. In the very first moments after the Big Bang, we are talking about an extremely small fraction of the first second. Something extraordinary happened. The universe underwent a phase of extremely rapid expansion called cosmic inflation. In a span of time shorter than the blink of an eye, perhaps only 10 to the power of minus 32 seconds, the universe expanded by a factor of at least 10 to the 26th power, meaning it increased in size at least 100 million trillion times. A region smaller than an atom suddenly became larger than a galaxy. And the strange thing, during inflation, space expanded faster than light. You might think, wait, nothing can be faster than light. And that is correct. No object can move through space faster than light. But space itself is not bound by that rule. Space can expand at any speed. So during inflation, regions of space were being separated at speeds faster than light could keep up with. Why did inflation occur? We are not entirely certain. The most widely accepted theory is that it was driven by a type of energy field called the inflaton field, which existed in the very first moments. When this field decayed, its energy was converted into matter and radiation, reheating the universe and ending inflation. But inflation, however brief, had far-reaching consequences. It explains why the universe looks uniform everywhere, because everything we see came from a tiny region that was stretched to enormous size. It explains why space is flat. Inflation smoothed out any curvature, like inflating a balloon makes its surface flatter. And most importantly, it explains the origin of structure in the universe. Galaxies, galaxy clusters, large-scale structures, all grew from tiny quantum fluctuations that inflation stretched up to cosmic scales. These fluctuations, tiny ripples in the energy density of the early universe, were the seeds from which all large-scale structure grew. And we can see their traces. Approximately 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. Before that, the universe was an opaque plasma, photons constantly colliding with free electrons. But when neutral atoms formed, photons were suddenly free to travel. And that light, from the moment the universe became transparent, is still traveling through the universe today. It is called the cosmic microwave background, CMB. The CMB is the oldest light we can observe. It comes from when the universe was only 380,000 years old, only 0.003% of its current age, and it is everywhere. In every direction you look, you see the CMB, light from the early universe, now redshifted down to microwaves by the expansion of space. If your eyes could see microwaves, you would see a soft, warm glow covering the entire sky, not from stars or galaxies, but from the universe itself. And when scientists measured the CMB with high precision, using satellites such as COBE, WMAP, and Planck, they saw something wondrous. The CMB is not perfectly uniform. There are tiny fluctuations in temperature, just a few parts per 100,000 of a degree. Some regions are slightly warmer, some slightly cooler. These fluctuations are not random. They are the traces of quantum ripples from inflation, the seeds from which galaxies would grow. Regions that were slightly denser, warmer in the CMB, had slightly stronger gravity. Over millions and billions of years, they pulled in more matter, grew larger, became clouds of gas, then the first stars, then galaxies. So when you look at a map of the CMB, a temperature map of the universe, when it was only 380,000 years old, you are looking at the blueprint for all structure in the universe today. You are looking at the seeds of the Milky Way, of Andromeda, of every galaxy we see, and you are looking at direct evidence of inflation. The specific pattern of fluctuations matches exactly what inflation predicts. So, we have a coherent story of the early universe. It began with the Big Bang, the birth of time and space. In a tiny fraction of the first second, inflation stretched a small region to enormous size, creating a uniform, flat universe with tiny fluctuations. When inflation ended, energy converted into matter and radiation. The universe was a hot, dense plasma. Over hundreds of thousands of years, it expanded and cooled. At 380,000 years, atoms formed, and light, the CMB, was released. The tiny fluctuations in the CMB were the seeds for structure. Gravity amplified them. Gas accumulated. The first stars formed, and over billions of years, larger structures gradually grew. Galaxies, galaxy clusters, superclusters, developing into the cosmic web we see today. All of it can be traced back to the very first moments after the Big Bang. Space is expanding, carrying galaxies farther away. And in the distant future, they will be so far away that light can no longer travel between them. Each galaxy will become isolated in darkness. But now, we live at a special moment, when the universe is still young enough to see light from distant galaxies, when we can study the CMB and learn about the deep past. There is a profound secret in the universe, a secret that scientists discovered when they realized that what we see is only a small fraction of what actually exists. All the stars, all the galaxies, all the planets, all the gas and dust, everything that emits light, reflects light, or absorbs light, all ordinary matter we know of makes up only about 5% of the universe. Only 5%. The remaining 95% is something else, something invisible, something mysterious. And the largest portion of that, approximately 27% of the total energy of the universe, is something called dark matter. Dark matter does not emit light. It does not absorb light. It does not reflect light. It is completely invisible to every type of telescope we have. So how do we know it exists? Because it has gravity. And gravity is something we can measure. In the 1930s, the astronomer Fritz Zwicky was studying the Coma Cluster, a group of more than 1,000 galaxies bound together by gravity. He measured the speeds of these galaxies as they moved through the cluster, and he calculated the total mass the cluster would need to hold those galaxies together at such speeds. The result astonished him. The required mass was approximately 400 times greater than the mass of all the stars and gas he could see. There was an enormous amount of invisible matter there, holding the cluster together. Zwicky called it dunkel materie, dark matter, but his discovery was ignored for decades. Until the 1970s, when the astronomer Vera Rubin was studying spiral galaxies. Spiral galaxies rotate like enormous spinning disks of stars and gas rotating around a center. And according to the laws of physics, stars at the outer edge, further from the center, should move more slowly than stars near the center, just as the outer planets in the solar system move more slowly than the inner ones. But when Rubin measured the rotation speeds, she found something strange. Stars at the outer edge were moving just as fast as stars near the center. The rotation curve was flat, not declining as predicted. This meant there had to be more mass at the outer edge, invisible mass, to provide the gravitational force needed to keep those stars in orbit. Without dark matter, stars at the edge would fly out of the galaxy. They were moving too fast to be held in place by the gravity of visible matter alone. Dark matter forms a halo surrounding each galaxy, extending far beyond the visible stars. And this halo contains more mass, typically 5 to 10 times more, than all the stars and gas. So when you look at the Milky Way, that band of starlight across the night sky, you are only seeing a small part. Most of the galaxy's mass is invisible, spread through an enormous halo around what we can see. And evidence for dark matter comes from many other sources. Gravitational lensing, the bending of light by gravity. When light from a distant galaxy passes near a large galaxy cluster, the light is bent by the cluster's gravity. The image of the distant galaxy is distorted, stretched into arcs or multiple images. By measuring the degree of bending, scientists can calculate the total mass of the cluster. And again, the total mass is many times greater than the mass of visible matter. The Bullet Cluster, a famous galaxy cluster, shows dramatic evidence. This is two galaxy clusters that collided and passed through each other. Hot gas from the two clusters, visible in X-rays, collided and was slowed down. But the dark matter, not interacting with light or gas, passed through unimpeded. Gravitational lensing shows that most of the mass is not where the gas is, but ahead, where the dark matter has already passed through. This is direct evidence that dark matter exists and is separate from ordinary matter. So what is dark matter? We do not know for certain. It is one of the greatest mysteries in physics. It is not dim stars, or planets, or cold gas. We have looked for those, and there are not enough to explain it. It is not black holes. We would see their effects through gravitational lensing in a different way. The most widely accepted theory is that dark matter is made of a new type of undiscovered elementary particle, possibly WIMPs, weakly interacting, massive particles, or axions, much lighter particles. These particles would interact only through gravity and possibly through the weak force, but not through electromagnetism, which is why they are invisible. And if the theory is correct, trillions of dark matter particles are passing through your body every second right now. They pass through the Earth, through you, through everything, interacting almost not at all. Scientists are trying to detect them with extremely sensitive detectors deep underground to avoid interference. But so far, no direct confirmed detection has been made. Dark matter remains a mystery, but it is real. We see its effects everywhere in the universe, and it plays a critical role in the structure of the universe. After the Big Bang, dark matter began to clump together due to gravity earlier than ordinary matter. It formed gravitational seeds, denser regions, that ordinary matter then fell into. Over billions of years, dark matter formed an enormous network, the cosmic web. This network looks like a mesh or soap foam with long filaments, nodes where they intersect, and large voids in between. The filaments, made primarily of dark matter, stretch hundreds of millions of light years, connecting galaxy clusters to one another. Ordinary matter, gas and stars, accumulates along these filaments, forming galaxies at the intersections. The nodes, where many filaments meet, are where the largest galaxy clusters form, containing thousands of galaxies bound together by the gravity of dark matter. And between the filaments are voids, enormous empty spaces, hundreds of millions of light years wide, containing very few galaxies. The Milky Way lies on one of these filaments, part of the Laniakea supercluster, an enormous structure containing approximately 100,000 galaxies, stretching 520 million light years. And all of this, the entire cosmic web, is held together by dark matter. It is the invisible skeleton of the universe. But there is an even more mysterious component, one that is even more dominant: dark energy. In the late 1990s, astronomers were studying distant supernovae, stellar explosions with predictable brightness, used as standard candles to measure cosmic distances. They expected to find that the expansion of the universe was slowing down due to the gravity of all the matter in the universe pulling back. But they found the opposite. The universe was expanding faster and faster. This was shocking. It was like throwing a ball into the air and watching it accelerate upward instead of slowing down and falling back. Something was pushing the universe to expand faster, a force opposing gravity. They called it dark energy, not because it is dark, but because we do not know what it is. And dark energy is not small. It accounts for approximately 68 to 70% of the total energy mass of the universe. So the universe is made of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. 95% of the universe is things we cannot directly see and do not fully understand. Dark energy acts like a repulsive force in space. Unlike matter and gravity, which pull things together, dark energy pushes space to expand. And unlike matter, the density of dark energy does not decrease as space expands. It remains constant, or nearly constant, per cubic meter of space. This means that as the universe expands, the total amount of dark energy increases, and that makes the expansion accelerate even further. In the distant future, hundreds of billions of years from now, dark energy will push galaxies so far apart that light cannot travel between them. Each galaxy will become completely isolated. Eventually, If dark energy continues to intensify, it may even tear apart galaxies, stars, and even atoms, a scenario called the Big Rip. But that is very far away, and we are not certain whether it will happen. What is dark energy? Once again, we do not know. The simplest explanation is that it is a cosmological constant, a fundamental property of space itself. Every cubic meter of space has a small inherent amount of energy. And as space expands, there is more space, so there is more energy. Einstein actually predicted this. He added a cosmological constant to his general relativity equations. But then he removed it, calling it his greatest mistake. It turns out it may have been correct. Or dark energy may be a type of dynamic energy field called quintessence that changes over time and space. We do not know. It is one of the greatest questions in physics and cosmology. Dark matter, comprising 85% of all matter, holds galaxies together, forms the skeleton of the cosmic web, and guides the formation of large-scale structure. Dark energy, comprising 70% of the total energy of the universe, pushes space to expand faster. And we, made of ordinary matter, are only a small fraction. We are the rare 5% that can emit light, can be seen, can think, and wonder. But we exist in a universe far larger, far more mysterious than what our eyes can see. The universe is still full of secrets, and that is part of what makes it wondrous. Right now, as you lie here, you are moving. Not only because Earth is rotating on its axis, though it is spinning at approximately 1,670 kilometers per hour at the equator. Not only because Earth is orbiting the Sun, though it is moving at approximately 107,000 kilometers per hour, but because the entire solar system, the Sun, Earth, all the planets, is moving through space at an incredible speed. We are orbiting the center of the Milky Way at approximately 828,000 kilometers per hour, or about 230 kilometers per second. That is nearly 500,000 miles per hour, more than 450 times the speed of a bullet. And that speed is not random. It is precisely the speed needed to keep us in orbit, a balance between the gravitational pull toward the galactic center and the centrifugal force from our motion. If we moved more slowly, we would spiral inward toward the center. Faster, and we would fly out of the galaxy. But at 230 kilometers per second, we are in a stable orbit, a nearly perfect circle approximately 26,000 light-years from the galactic center. And how long does that orbit take to complete? Approximately 225 to 250 million years. That is our cosmic year, the time for the solar system to complete one full orbit around the Milky Way. Let that sink in. Every 250 million years, we return to where we are right now in the galaxy. Since Earth formed, 5 billion years ago, we have orbited the galaxy approximately 18 to 20 times. The last time we were at this position in the galaxy, 250 million years ago, dinosaurs had not yet evolved. Land creatures were mainly amphibians and early reptiles. Pangaea, the single supercontinent, was still intact. And the next time we return here, In another 250 million years, Earth will be unrecognizably different. The continents will be in different positions. Life will have evolved along unpredictable paths, and perhaps humanity, if it still exists, will have changed completely. But our journey is not just a simple circle. As we orbit the galaxy, we also move up and down, oscillating through the plane of the galactic disk like a horse on a carousel. Right now, we are north of the galactic plane, moving northward. In approximately 30 million more years, we will reach the highest point, about 230 light-years above the plane. Then, we will fall back down, pass through the plane, go below, and come back up again. The complete cycle takes approximately 60 to 70 million years, and some scientists have speculated that when we pass through the galactic plane, where the density of stars and matter is highest, gravity may disturb the Oort cloud, the distant region of the solar system containing billions of comets, sending some comets into the inner solar system, increasing the risk of impacts with Earth. This may explain some of the mass extinction cycles in Earth's history, but this remains a hypothesis under debate. So we are not simply orbiting the galaxy. We are dancing, up and down, in a wide circle, over billions of years. But the journey does not stop there. The Milky Way itself is also moving. The entire galaxy, with its hundreds of billions of stars, is flying through space at approximately 600 kilometers per second relative to the cosmic microwave background radiation, CMB. We are moving toward a region of space called the Great Attractor, an enormous concentration of gravitational force approximately 150 million light-years away. But even the Great Attractor is being pulled by a larger structure, the Shapley supercluster, more than 650 million light-years away. And all these structures, the Milky Way, the Great Attractor, the Shapley supercluster, are part of an even larger structure called Laniakea, an enormous supercluster of galaxies containing approximately 100,000 galaxies, stretching 520 million light-years. So we are moving in a complex system of nested motions, Earth rotating, Earth orbiting the Sun, the solar system orbiting the galaxy flying through space, pulled by larger and larger structures. All simultaneously, all without pause. And within all these motions, something special is approaching, an event that will dramatically change the night sky. The Milky Way and the Andromeda Galaxy are moving toward each other. Andromeda, the largest spiral galaxy nearest to us, is currently 2.5 million light-years away. It is the most distant object you can see with the naked eye, a faint smudge in the night sky. But Andromeda is approaching. It is moving toward us at approximately 110 kilometers per second, about 400,000 kilometers per hour. This means that in approximately 4 to 5 billion years, Andromeda and the Milky Way will collide. But collision is a misleading word. It suggests a violent crash with stars smashing into each other. The reality will be far gentler and far more wondrous. As the two galaxies draw close, their gravity begins to pull and distort each other. The spiral arms will be stretched, deformed. Some stars will be flung out into intergalactic space. Some will be pulled into new orbits. The two galaxies will pass through each other, or nearly through each other, for the first time. But gravity will pull them back. They will return, collide a second time, orbiting in complex patterns around each other. And over billions of years, perhaps 5 to 6 billion years from the first encounter, the two spiral galaxies will slowly merge into a single, larger elliptical galaxy. Astronomers have already named this future galaxy Milkometa, a combination of Milky Way and Andromeda. But here is the fascinating part. Throughout this entire process, almost no stars will actually collide with each other. Why? Because stars are separated by enormous distances. Even within a galaxy, where stars appear crowded, the distances between stars are vast. The nearest star to us, Proxima Centauri, is 4.2 light-years away. If the Sun were the size of an orange, Proxima Centauri would be another orange approximately 6,000 kilometers away. So, when two galaxies collide, the stars mostly pass through each other, like two clouds passing through each other. They do not touch. The space between stars is too vast, but the orbits of stars will be changed by the overall gravitational field. Our solar system may be flung further from the center of the new galaxy, or closer, or even thrown out of the galaxy entirely, becoming a wandering star in intergalactic space. But Earth and the solar system will likely survive unharmed. The planet still orbiting the Sun, even as the Sun orbits the new center of Milkometa, and the night sky will look completely different. Instead of the milky band of the Milky Way, the sky may be filled with scattered stars, some closer, some further, in an elliptical distribution rather than a flat disk. The Andromeda Galaxy, once a faint distant smudge, will no longer be a separate galaxy. It will be part of our galaxy. And in fact, a few billion years before the merger is complete, Andromeda will grow larger in the night sky. It will become a large ellipse, gradually covering a large portion of the sky as it draws closer. Sky watchers in the future, if humans or other forms of life still exist, will witness a magnificent spectacle. Two galaxies dancing, deforming, merging in a process lasting billions of years. But there is one variable, the Sun. The Sun, like all stars, does not last forever. It is burning hydrogen in its core, converting it into helium. In approximately 5 billion more years, the Sun will exhaust its core hydrogen. The core will contract and heat up. The outer layers will expand. The Sun will become a red giant. It will grow so large that it will swallow Mercury, Venus, and possibly Earth. So the Andromeda collision, occurring in 4 to 5 billion years, will happen around the same time the Sun becomes a red giant. If Earth survives, perhaps pushed into a more distant orbit by the Sun's loss of mass as it releases its outer layers, the sky will be a strange spectacle. An enormous red sun dominating most of the sky, and Andromeda, or its merging remnants, spread across the night sky. But all of this is in the distant future. By that time, humanity, if it still exists, will have evolved or changed beyond recognition, or will have moved to other stars, or will have long since disappeared. What we know for certain is that galaxies are not static. They move, they dance, they collide and merge. And this is not rare. Throughout the universe, galaxies are constantly merging, smaller galaxies being swallowed by larger ones, galaxies of similar size colliding and forming vast new galaxies. The Milky Way itself has swallowed many smaller galaxies in the past. and it is still swallowing some, such as the Sagittarius dwarf galaxy, which is being torn apart by our gravity. The universe is a dynamic place. Nothing stands still. Everything is moving, changing, evolving. There are places in the universe where light becomes so extreme as to be almost unbelievable, where energy is released with an intensity that surpasses anything we can imagine. Let us begin with quasars, the brightest, most powerful, most enduring objects in the universe. Quasar is short for quasi-stellar radio source. When they were first discovered in the 1960s, they looked like stars in photographs, small bright points. But when astronomers measured their redshift, they realized something astonishing. Quasars are extremely distant, billions of light years away. And if they are that far away, but still bright enough to see, they must be extraordinarily luminous, hundreds to thousands of times brighter than an entire typical galaxy. A single quasar, an object far smaller than a galaxy, can be brighter than 100 to 1,000 billion stars. How can something be that bright? The answer lies at the center, a supermassive black hole. At the center of most large galaxies, including the Milky Way, there is an enormous black hole with a mass millions to billions of times the mass of the Sun. Most of the time, these black holes are relatively quiet. Not much matter is falling in. But in some galaxies, especially in the early universe, when matter was denser, large quantities of gas and dust fall into the black hole. As matter falls toward the black hole, it does not fall straight in. Instead, it forms a spiraling disk, an accretion disk, orbiting the black hole, gradually spiraling inward. In this disk, matter moves extremely fast, near the speed of light. Friction between particles generates enormous heat, millions of degrees, and matter that hot emits light, enormous amounts of light. The accretion disk surrounding a supermassive black hole becomes one of the most powerful light sources in the universe. That is a quasar. A quasar is not the black hole itself. The black hole does not emit light. It is the region surrounding the black hole, where matter is falling in, heating up, and shining with terrifying intensity. And some quasars also have jets, streams of matter shooting out from near the black hole, perpendicular to the disk, at speeds close to light. These jets can extend millions of light years into space, pumping energy and particles into the surrounding environment. Quasars were most common in the early universe, approximately 10 to 12 billion years ago. When galaxies were young, matter was denser, and supermassive black holes were actively consuming matter. Today, quasars are rarer. Most supermassive black holes have consumed the nearby matter and are now quiet. But in the distant past, the universe was filled with quasars, the brightest beacons, illuminating the surrounding space with unimaginable intensity. And when we look at distant quasars, we are looking back in time, seeing the universe when it was younger, more dynamic, more violent. But there are even more extreme sources of light, though only fleeting. Gamma-ray bursts, GRBs, are the most powerful flashes of energy in the universe. In a matter of seconds, sometimes only a few tenths of a second, a GRB releases more energy than the sun will emit over its entire 10 billion year lifetime. During those seconds, a GRB is brighter than everything else in the observable universe. If you had eyes that could see gamma rays, You would see it outshine all the stars, all the galaxies combined, and then it goes out, disappears, leaving only a fading afterglow. GRBs occur when a massive star, at least 20 to 30 times the mass of the Sun, reaches the end of its life and collapses into a black hole. The core of the star collapses extremely rapidly. The outer layers fall inward, and in a brief moment, an enormous amount of energy is released. Most of this energy radiates equally in all directions. That is a supernova, the stellar explosion we have heard of. But in some rare cases, a portion of the energy is concentrated into two narrow jets, firing out from the poles of the collapsing star. These jets, only a few degrees wide, contain enormous energy focused into a narrow beam. And if one of those jets happens to point toward Earth, we see it as a GB. So a GERB is a lighthouse effect. They occur more frequently than we observe, but we only see the ones whose beams point toward us. Fortunately, GRBs are extremely distant. Most are billions of light years away. So even with their terrifying intensity, they are not dangerous to us. But if a GRB occurred nearby, within a few thousand light years, and pointed toward us, it could be catastrophic. The gamma rays would destroy the ozone layer, allowing solar radiation to harm the surface, causing mass extinction. Some scientists speculate that one or more extinction events in Earth's history may have been caused by a nearby GRB. But there is no confirmed evidence. What we know for certain is that GRBs are the most powerful, briefest, most extreme events in the universe. Flashes of light in the darkness, telling the story of dying stars at great distances. But the universe has not always had these powerful lights. There was a period, a long period, when the universe was plunged in complete darkness. After the Big Bang and the inflationary period, the universe was a hot, bright plasma, particles moving extremely fast, photons flying through. But over hundreds of thousands of years, the universe expanded and cooled. At 380,000 years, neutral atoms formed. Light, the CMB, was released. And then, nothing. No stars, no galaxies. Only hydrogen and helium gas. Filling space. Opaque, dark. The universe entered a dark age, lasting hundreds of millions of years. During this period, no light was produced. Only the CMB, now shifted to infrared by redshift and darkness. But in that darkness, something was happening. Gravity was pulling gas into denser regions. Dark matter, invisible but real, was creating gravitational seeds, and gas was falling into them. Over tens of millions of years, these regions became denser. Gas compressed. Temperatures rose. And finally, approximately 100 to 200 million years after the Big Bang, temperatures and density were high enough for fusion to begin. The first light switched on. The first stars, called population 3 stars, formed. And they were unlike any stars that exist today. They were enormous, possibly 100 to 300 times the mass of the Sun, because there were no heavy elements to cool the gas and allow smaller stars to form. They were extremely hot and bright, blue-white. millions of times brighter than the sun. And they were short-lived, only a few million years, rather than billions of years like the sun. But in those few million years, they did one important thing. They created the first heavy elements. In their cores, hydrogen and helium were fused into carbon, oxygen, silicon, iron, the elements needed for planets and life. And when these stars died, exploding as supernovae, they scattered these elements into space, enriching the next generation of stars. So the first stars, though they lived only briefly, were extremely important. They transformed the universe from a place with only hydrogen and helium into a place with the complex elements needed for everything else. And their light did one other thing. It began reionization. After neutral atoms formed at 380,000 years, the universe was filled with neutral hydrogen, complete atoms with electrons bound to protons. Neutral hydrogen absorbs certain wavelengths of light, making the universe slightly opaque, like fog. But light from the first stars, especially ultraviolet radiation, carried enough energy to strip electrons from hydrogen atoms. Neutral atoms became ionized again. Protons and electrons separated. An ionized gas is transparent to light. The fog lifted. Over hundreds of millions of years, as more and more stars formed, ionized regions expanded, transparent bubbles around early stars and galaxies. These bubbles grew, met, and merged. And approximately 1 billion years after the Big Bang, reionization was complete. The entire universe became ionized and transparent as it still is today. This is the awakening of the universe, the cosmic dawn, when the first stars ignited after hundreds of millions of years of darkness, creating the first heavy elements and making the universe transparent. And we can see traces of this process. The James Webb Space Telescope, launched in 2021, was specifically designed to look into this era. It can observe infrared light, light from the most distant stars and galaxies, redshifted from visible wavelengths into the infrared. And it is discovering galaxies from when the universe was only a few 100 million years old, close to the time when the first stars formed. These galaxies are small, chaotic, filled with bright blue young stars. They are the ancestors of today's large galaxies. And by studying them, we learn about the cosmic dawn, how the universe transitioned from darkness to light, from simplicity to complexity. The universe is not silent. It is sending messages, billions of messages, every second, in every direction, in every form. And right now, while you are lying here, your body is being penetrated by those signals. Most of them you cannot feel. Most pass through you as if you do not exist, but they are there, and they tell stories about distant places, about violent events, about the fundamental nature of the universe. Let's begin with cosmic rays. The name is misleading. They are not rays in the sense of light photons. They are particles, mostly protons, but also some heavier nuclei and electrons. And they move fast, very fast. Most cosmic rays travel at speeds close to the speed of light, 99% of it or more. Some, the rare ultra-high energy cosmic rays, travel at 9,999% of the speed of light, carrying energy comparable to a hard-thrown baseball, all concentrated in a single tiny particle. Where do these particles come from? Most lower energy cosmic rays come from the sun. The sun constantly emits charged particles, the solar wind, and sometimes releases stronger bursts during solar flare events. But higher energy cosmic rays come from farther away, from supernovae, from supernova remnants, where shock waves are still expanding and accelerating particles, from pulsars, from black holes consuming matter. And the ultra-high energy cosmic rays, the rarest and most powerful, may come from beyond our galaxy, from quasars, from active galaxies, from sources we still do not fully understand. Every second, thousands of cosmic rays strike Earth's atmosphere. When they collide with air molecules, nitrogen and oxygen, they create showers of secondary particles, muons, pions, electrons, cascading down to the surface. Some of these secondary particles reach the ground. Some are passing through you right now. Every second, hundreds of muons, a type of particle similar to electrons but heavier, pass through your body. They go through you as if you were air. Most do not interact with any of your atoms. They are harmless, but they are there. Messages from violent events far away, now quietly passing through you in the night. Cosmic rays are not just scientific curiosities. They have real effects. They can flip bits in computer memory, causing random software errors. Airplanes at high altitudes and astronauts in space receive higher doses of radiation from cosmic rays. And some scientists speculate that cosmic rays may have played a role in evolution, causing mutations in DNA, creating the genetic variation on which natural selection acts. So these tiny particles, coming from supernovae thousands of light years away, may have helped shape life on Earth. But there are other particles passing through you even more frequently and interacting even less. Neutrinos. Neutrinos are ghostly particles. They have no electric charge. They have an incredibly small mass, almost zero, and they barely interact with matter. A neutrino can pass through the entire Earth, through 13,000 kilometers of rock and metal, with a very high chance of not colliding with a single atom. And they come from everywhere. The Sun is the largest nearby source of neutrinos. In the Sun's core, fusion turns hydrogen into helium, and this process produces billions of neutrinos. These neutrinos stream outward in all directions at nearly the speed of light. Because the Sun is so close, just 8 light minutes away, and produces so many neutrinos, the Earth is constantly bathed in them. Every second, about 100 billion solar neutrinos pass through each square centimeter of Earth. And since your body has a surface area of about 2 square meters, 20,000 square centimeters, about 2 trillion solar neutrinos pass through you every second. 2 trillion every second. During the day, they come from the direction of the Sun and pass through you. At night, they pass through the entire Earth first, then through you from below, and you feel nothing. They pass through you as if you were empty space. But neutrinos do not come only from the Sun. Whenever a supernova explodes, when a massive star collapses and explodes, most of the energy released is not in light, but in neutrinos. In the few seconds of collapse, 99% of the star's energy is carried away by a flood of neutrinos. Tens of billions of trillions of neutrinos emitted in all directions. In 1987, a supernova exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 168,000 light-years away. A few hours before the light from the supernova reached Earth, neutrino detectors recorded a brief burst, about 25 neutrinos in a few seconds. Out of the trillions upon trillions of neutrinos that passed through Earth, only 25 interacted with the detectors. But those 25 were enough to confirm supernova theory and marked the first direct detection of neutrinos from a supernova. And there are neutrinos from even farther away, from the Big Bang. Just like the cosmic microwave background, light from 380,000 years after the Big Bang, there should also be a cosmic neutrino background from just 1 second after the Big Bang. These neutrinos fill the universe, about 330 neutrinos per cubic centimeter of space. They pass through you, through the Earth, through everything, continuously, but they have very low energy, too low to be detected with current technology. We know they must be there based on theory, but we have not directly detected them yet. However, neutrinos are not the only type of signal from the universe. There are also radio waves. Radio waves are a form of light, electromagnetic waves with longer wavelengths than visible light. And the universe emits radio waves from many sources. One of the strangest sources is pulsars. A pulsar is a rotating neutron star and dense remnant of a massive star after it explodes as a supernova. A neutron star is only about 20 kilometers across, smaller than a city, yet it contains more mass than the sun. A teaspoon of neutron star material would weigh about 1 billion tons. And it spins fast. Some pulsars rotate hundreds of times per second. A neutron star has an extremely strong magnetic field, trillions of times stronger than Earth's. And as it spins, the magnetic field rotates with it, producing beams of radiation, mainly radio waves, emitted from its magnetic poles. If a beam points toward Earth, we observe a brief pulse each time it sweeps past, like a lighthouse. Pulse, 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 as regular as a clock. When pulsars were first discovered in 1967 by Jocelyn Bell Burnell, the pulses were so regular that scientists briefly wondered whether they might be signals from extraterrestrial civilizations. They even named the first source LGM-1, Little Green Men 1. But as more pulsars were found, it became clear they were natural phenomena, rotating neutron stars, and pulsars are incredibly precise clocks. Some, especially millisecond pulsars that rotate hundreds of times per second, are as stable as our best atomic clocks. Scientists can use networks of pulsars as a kind of cosmic GPS, pulsar timing arrays, to detect extremely long gravitational waves from merging supermassive black holes far away. But radio waves do not come only from pulsars. Galaxies emit radio waves, especially those with active black holes at their centers. Jets from these black holes, streams of matter launched at nearly the speed of light, produce strong radio emission. Supernova remnants emit radio waves as their shock waves expand through space. Even planets, like Jupiter, emit radio waves due to electrons moving within their magnetic fields. And then there are mysteries, fast radio bursts, or FRBs. FRBs are extremely short radio pulses, lasting only a few milliseconds, yet incredibly bright, coming from distant galaxies. They were first discovered in 2007 and for many years their origin was a complete mystery. Today, we think most FRBs come from magnetars, a type of neutron star with an extremely strong magnetic field, possibly 1,000 times stronger than that of a typical pulsar. Sometimes, a magnetar's magnetic field suddenly rearranges, a starquake, releasing an enormous amount of energy in a brief flash, observed as an FRB. But some FRBs repeat, emitting multiple bursts from the same source, suggesting that the source is not destroyed and may remain active for long periods. These repeating FRBs are still an active area of research. And all of these signals, cosmic rays, neutrinos, radio waves, come from distant events and objects, carrying news about the universe. We live in a sea of cosmic signals. Most of them we cannot see or feel, but they are there, constant, invisible, carrying the stories of the universe. Each cosmic ray tells of a supernova explosion, a shock wave, a particle accelerated to near light speed. Each neutrino tells of fusion in the core of a star, of a distant supernova, of the Big Bang itself. Each radio wave tells of a spinning pulsar, an active galaxy, a bursting magnetar. The universe is speaking. And we, with telescopes, detectors, and antennas, are learning how to listen. Hundreds of cosmic rays pass through you, coming from violent events far away. Explosions, shock waves, feeding black holes, and radio waves, invisible to the eye, are vibrating all around you, carrying pulses from pulsars spinning hundreds of times per second, from galaxies with jets blasting at near light speed. You do not feel them, but they are there. You are bathed in the signals of the universe, and that means you are never truly alone. You are constantly connected to the vast universe, through particles, through waves, through messages passing through you every second. The universe is touching you, gently, invisibly, but truly. When you look at the night sky, you see stars scattered, some near, some far, seemingly random, without any clear pattern. But if you zoom out, if you look at the universe on a larger scale, much larger, a pattern emerges. Galaxies are not randomly distributed. They cluster. They form groups. Groups connect to one another, and between them are vast regions, nearly empty voids. The universe has structure, and that structure is unimaginably vast. Let's begin with our home, the Milky Way. The Milky Way is not alone. It is part of the local group, a small cluster of about 80 galaxies, spanning roughly 10 million light-years. Within the local group, there are 3 large galaxies: the Milky Way, Andromeda, and Triangulum. The rest are mostly dwarf galaxies, much smaller, with fewer stars. And the local group is part of a larger structure, the Virgo supercluster, containing hundreds of galaxy groups and clusters, extending about 110 million light-years. But even the Virgo supercluster is only part of an even larger structure, one discovered and mapped only in the past decade: Laniakea. The name Laniakea comes from Hawaiian, meaning immense heaven or immeasurable sky, and it is a fitting name for such a colossal structure. Laniakea is a supercluster of galaxies, a collection of galaxy clusters bound together by gravity, all moving along the same cosmic flow. It contains around 100,000 galaxies, including the Milky Way, Andromeda, and tens of thousands of others. It spans about 520 million light-years, 5 times larger than the Virgo supercluster. And its total mass? About 100 quadrillion times the mass of the Sun. Most of it is dark matter, but there is still enough normal matter to form around 100,000 galaxies. But Laniakea is not a uniform structure. It has internal organization. At its center lies the Great Attractor, a region of space where gravity is extremely strong. All galaxies within Laniakea are being pulled toward it. The Milky Way, located on the outer edge of Laniakea, is moving toward the center at about 600 kilometers per second. But we will never reach it, because space is expanding faster than we can travel. Laniakea itself is stretching, and eventually its most distant parts will be pushed so far apart that light can no longer travel between them. But Laniakea is just one of many superclusters, and these superclusters are not randomly distributed. When astronomers map millions of galaxies in the observable universe, a pattern emerges, a beautiful, complex pattern, like a three-dimensional web or soap foam. The cosmic web. Galaxies gather along long, thin filaments, stretching hundreds of millions of light-years. These filaments connect massive galaxy clusters like bridges or highways. At the intersections of multiple filaments, the nodes, the largest galaxy clusters form, containing thousands of galaxies, and between the filaments are vast regions, cosmic voids, almost empty. This is the largest structure in the universe, the cosmic web, spanning the entire observable cosmos. Let's begin with the filaments. Filaments are composed mostly of dark matter, accounting for about 80 to 85% of their mass. Dark matter forms the gravitational scaffolding. Ordinary matter, hydrogen and helium gas, falls into these filaments, pulled by the gravity of dark matter. Along the filaments, gas accumulates, cools, and eventually forms stars and galaxies. So filaments are not static structures. They are highways along which matter flows, where galaxies form and drift. Some filaments are over 500 million light-years long, 500 million light-years. Light itself takes 500 million years to travel from one end to the other, and they are thin, only tens of millions of light-years across. Imagine a thread hundreds of meters long, but only a few millimeters wide. That is the scale of cosmic filaments. And along these threads, galaxies line up like beads on a string. Astronomers have mapped several enormous filaments. The Sloan Great Wall is one of the largest known structures, stretching over 37 billion light-years and containing tens of thousands of galaxies arranged along a massive filament. The Hercules Corona Borealis Great Wall is even larger, possibly extending up to 10 billion light-years, though its structure is still debated. These structures are almost beyond comprehension. Light takes billions of years to cross them. Even traveling at the speed of light, it would take nearly the age of the universe to traverse the Hercules Corona Borealis Great Wall. And at the intersections of filaments, where many strands meet, gravity becomes extremely strong. Matter falls in from multiple directions, forming the largest galaxy clusters. The Coma Cluster contains over 1,000 large galaxies and perhaps 10,000 smaller ones, all bound within a region about 20 million light-years across. It lies at a node of the cosmic web where multiple filaments intersect. And between all these structures, between filaments, between clusters, are the voids. Cosmic voids. Voids are regions of space that are nearly empty, containing very few galaxies and very little matter. They are not completely empty. They still contain dark matter and some gas, but the density is extremely low, perhaps only 10% of the average density of the universe, and they are large, very large. The Boötes void, also known as the Great Nothing, is about 330 million light-years across. In a region large enough to contain thousands of galaxies, the Boötes void contains only around 60, most of them small and faint. Why do voids exist? They form from the way matter clumps together. In the early universe, matter was distributed almost uniformly, but with tiny fluctuations. Some regions slightly denser, some slightly less so. Over time, gravity pulled matter from less dense regions into denser ones. Dense regions became denser, forming filaments and clusters. Less dense regions became emptier, forming voids. Dark matter flows from voids into filaments, like water flowing from hills into valleys. And as dark matter moves, gas follows. The result is vast regions that are nearly empty, surrounded by walls of galaxies along filaments. And voids are not static emptiness. They are expanding. Space within voids expands faster than in filaments and clusters because there is less matter to slow the expansion. So over time, voids grow larger, filaments grow thinner, and the structure of the cosmic web becomes more pronounced. When you look at maps of the cosmic web, showing millions of galaxies and their positions, it resembles a neural network in the brain, or soap foam, or the structure of a sponge. There are long, thin strands, dense nodes, and large, nearly empty bubbles. And this pattern repeats across every scale we can observe, from small galaxy clusters to superclusters to the entire observable universe. The cosmic web is the largest structure in nature. Nothing is bigger. It is how the universe organizes itself on the grandest scales. And it all originates from tiny quantum fluctuations in the early universe, ripples stretched to cosmic scales by cosmic inflation. Those ripples became the seeds of structure. Gravity amplified them. Dark matter formed the framework. Ordinary matter fell in. And over 13.8 billion years, the cosmic web formed, a masterpiece of gravity and time. We live on a small planet, orbiting an average star, in a galaxy containing hundreds of billions of other stars. Our galaxy is one of about 80 in the local group. The local group is one of hundreds of groups in the Virgo supercluster. The Virgo supercluster is one of many clusters within Laniakea, and Laniakea itself is just a small node on a filament of the cosmic web, a network stretching across the observable universe, containing trillions of galaxies. We are only a tiny part of an unimaginably vast structure, one shaped over billions of years by gravity, dark matter, and the expansion of space. We are part of the cosmic web, connected to every other galaxy, every other cluster, through invisible threads of dark matter and gravity. The universe has order, and that order emerges from simple laws: gravity, expansion, time, operating over billions of years. The universe has not always been as it is today. It has changed. It is changing, and it will continue to change. The universe has a history, a story spanning 13.8 billion years, from the first moment to today and far into the future. And throughout that history, a continuous process has unfolded. Cosmic evolution. Let's begin at the beginning and follow the story. 13.8 billion years ago. The Big Bang. Time and space came into existence. The universe was an extremely hot, extremely dense point. In less than a fraction of a second, cosmic inflation. Space expanded faster than light, stretching a region smaller than an atom to enormous size. Tiny quantum fluctuations were stretched to cosmic scales, the seeds of all future structure. A few seconds after the Big Bang, the universe cooled enough for fundamental particles, quarks, and electrons to combine into protons and neutrons. These protons and neutrons form simple hydrogen and helium nuclei. This was Big Bang nucleosynthesis. Within the first 3 minutes, about 75% of matter became hydrogen and 25% became helium. That ratio still holds today. Most ordinary matter is hydrogen, followed by helium, with only trace amounts of everything else. 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. Light, the cosmic microwave background, was released. The universe became transparent for the first time. And then, darkness, the Dark Ages. No stars, no galaxies, only dense, dim, hydrogen and helium gas drifting through expanding space. But gravity was at work. Dark matter, present from the beginning, invisible but real, was clumping into dense regions. And gas was falling into those regions. 100 to 200 million years after the Big Bang, the cosmic dawn. The first stars ignited, massive, hot, bright, and short-lived. They lived only a few million years, but during that time, they did something crucial. In their cores, fusion created the first heavy elements: carbon, oxygen, silicon, iron, the elements necessary for planets and life. And when these stars died, exploding as supernovae, they scattered those elements into space. So the cycle began, a cycle that continues today. A star forms from a cloud of gas. It lives, burning fuel in its core, creating heavier elements. It ages, and eventually, it dies. A small star, like the sun, dies gently, shedding its outer layers as a planetary nebula, leaving behind a hot core called a white dwarf. A more massive star, at least 8 to 10 times the mass of the sun, dies violently. Its core collapses. Its outer layers explode. A supernova, one of the brightest events in the universe, releases energy and heavy elements into space. The remaining core becomes a neutron star, or, if massive enough, a black hole. And the heavy elements released: carbon, nitrogen, oxygen, iron, gold, uranium, mix with gas in the interstellar medium. That gas, now enriched with heavy elements, eventually collapses again to form new stars. These stars are born with heavy elements already present. Unlike the first stars, which had only hydrogen and helium. And when these stars die, they create even more heavy elements. the cycle repeats. Over billions of years, the universe becomes increasingly enriched with heavy elements. The first generation of stars had only hydrogen and helium. The second had some carbon and oxygen. The third had more. The Sun, a third or fourth generation star, contains about 2% heavy elements. And that 2% is crucial because it allows rocky planets like Earth to form. So every carbon atom in your body, every oxygen atom you breathe, every iron atom in your blood, all were forged in the cores of stars that lived and died billions of years ago. You are literally made of stardust. Not metaphorically, literally. And while stars are living and dying, galaxies are evolving too. The first galaxies were small, only a few million or tens of millions of stars, chaotic, without clear structure. But over time, gravity pulls galaxies together. Small galaxies collide and merge, forming larger ones. This process, galaxy mergers, has occurred throughout cosmic history and continues today. The Milky Way itself is the product of many mergers. It has absorbed smaller galaxies in the past, and it is still consuming some, such as the Sagittarius dwarf galaxy, which is being torn apart by our gravity. When galaxies merge, many things happen. Gas clouds collide, compress, and trigger bursts of star formation, starbursts, where millions of new stars can form in just a few million years. The supermassive black holes at the centers of each galaxy eventually merge, forming a larger black hole. And the stars from both galaxies mix, forming a larger galaxy with a new shape, often elliptical rather than spiral. Over billions of years, galaxies grow larger through mergers. Small, spiral galaxies merge into larger spirals or into giant elliptical galaxies. And in the distant future, as we discussed, the Milky Way and Andromeda will merge, forming Milkomeda. So galaxies are not static. They are growing, changing, evolving. And they do not only contain stars and gas, they also contain something invisible but crucial: magnetic fields. Galaxies have magnetic fields that extend throughout their entire structure, across the disk, through the halo, and even out into intergalactic space. These fields are generated by the motion of electrically charged gas, plasma, within the galaxy. As the gas rotates, it creates electric currents, and currents generate magnetic fields. The magnetic field in the Milky Way is much weaker than Earth's, only a few microgauss compared to Earth's roughly half a Gauss. But it extends across enormous distances, thousands of light years, and it matters. Magnetic fields help shape how gas moves, how stars form, and how cosmic rays are accelerated and confined within galaxies. Without magnetic fields, galaxies would look and behave very differently. And just as Earth's magnetic field can reverse over time, galactic magnetic fields also change, amplified by gas motion, stretched and twisted by spiral arms, regenerated through complex dynamo processes. So, a galaxy is a complex system: stars, gas, dust, dark matter, black holes, magnetic fields, all interacting, all evolving. And all of this, star formation, stellar death, galaxy mergers, magnetic fields, is part of a larger story, the story of the universe. From the Big Bang to darkness to light to structure, from simplicity to complexity, from uniformity to diversity. 13.8 billion years ago, the Big Bang. Only energy and the most fundamental particles existed. In the first second, inflation. The universe expanded and the seeds of structure were planted. In the first 3 minutes, simple nuclei formed, hydrogen and helium. At 380,000 years, atoms formed. Light was released. At 100 to 200 million years, the first stars, the first light, the first heavy elements. A few 100 million years later, the first galaxies, small and chaotic. At about 1 billion years, reionization completed. The universe became transparent. Over the next billions of years, galaxies grew through mergers. The cosmic web became clearly defined. About 9 billion years after the Big Bang, the solar system formed. Earth was born. 13.8 billion years after the Big Bang, today. We are here, looking back at history, and the story continues. In the next few billion years, the Milky Way and Andromeda will merge. The Sun will become a red giant. Earth, if it survives, will become a very different world. In tens of billions of years, star formation will slow as gas is used up. Galaxies will be filled with old, dim stars. In hundreds of billions of years, dark energy will push galaxies so far apart that light can no longer travel between them. Each galaxy or cluster will become isolated in darkness. In trillions of years, the last stars will fade. The universe will grow dark. And in an unimaginably distant future, 10 to the power of 100 years or more, even black holes will evaporate through Hawking radiation. The universe will be cold, dark, nearly empty. Only isolated particles drifting through ever-expanding space. That is the far future. But it is not something to be sad about. Because right now, we live in the golden age of the universe, when stars are shining, when galaxies are forming, when life can exist. We are fortunate to exist in this era, between the cosmic dawn and the cosmic dusk, when the universe is still young, active, full of light and possibility. We have come far in understanding the universe. We know its age. We know how it formed. We know how it expands. We have mapped millions of galaxies and traced their history across billions of years. But the more we learn, the more we realize how much we do not know. Cosmology, the science of the universe, is still filled with unanswered questions, deep mysteries, and fundamental limits to what we can know. Redshift is the phenomenon where light from distant objects is stretched toward longer wavelengths, toward the red end of the spectrum. It happens because space itself is expanding. As light travels through expanding space, its wavelength stretches. Blue light becomes red, infrared becomes microwave, and the amount of redshift tells us two key things. First, it tells us distance. More distant objects have higher redshift because their light has traveled through more expanding space. Second, it tells us time. Light from a high redshift galaxy was emitted long ago, when the universe was younger. So, when we observe high redshift galaxies, we are looking back in time, seeing the universe as it once was. Astronomers measure redshift by observing spectral lines, characteristic fingerprints in the light from elements like hydrogen, helium, and oxygen. In laboratories on Earth, these lines appear at specific wavelengths, But in light from distant galaxies, they are shifted toward the red, appearing at longer wavelengths. By measuring this shift, astronomers calculate redshift, usually denoted as Z. A galaxy with Z equals 1 has its light stretched to twice its original wavelength, a 100% increase, and lies about 7 to 8 billion light-years away. A galaxy with Z equals 6 has its light stretched sevenfold, coming from over 12 billion light-years away, when the universe was only about 1 billion years old. The most distant galaxies ever discovered have Z greater than 13. Their light stretched 14 times from when the universe was only a few 100 million years old, just after the cosmic dawn. So redshift is a window into the past. It allows us to study the universe's history, not by guessing, but by directly observing galaxies as they once were. But there is a complication. To fully understand the relationship between redshift and distance, we need to know how fast the universe is expanding. And that is where the Hubble constant comes in. The Hubble constant, usually denoted as h0, measures the current rate of expansion of the universe. It tells us how fast a galaxy at a distance of 1 megaparsec, about 3.26 million light-years, is moving away from us. And here is the problem. We do not know exactly what h0 is. There are two main ways to measure it, and they give different results. The first method uses the cosmic microwave background, CMB. By measuring fluctuations in the CMB and applying cosmological models, scientists infer that h0 should be about 67 kilometers per second per megaparsec. The second method uses standard candles, objects with known intrinsic brightness, such as type 1a supernovae. By comparing their observed brightness with their true brightness, scientists determine distances, and from that calculate h0. This method gives a value of about 73 kilometers per second per megaparsec, a 9% difference. From 67 to 73 may sound small, but it is much larger than the uncertainties in each measurement, and it has major implications. If h0 is 73, the universe is expanding faster than we think, which means it is younger, perhaps only 12.5 billion years instead of 13.8 billion. But that creates a contradiction, because we observe stars older than 13 billion years. If h0 is 67, everything fits better with the standard model. But then why do local measurements give a higher value? There could be errors in one of the methods, although both have been carefully tested. Or there could be new physics, something we do not yet understand about how the universe works. Perhaps dark energy is not constant but evolves over time. Perhaps there are new undiscovered forces. This is known as the Hubble tension, and it is one of the biggest problems in modern cosmology. Scientists are actively working to resolve it, using new measurements, new telescopes, and new techniques. But so far, the tension remains. And it reminds us that even the most fundamental things, like the expansion rate of the universe, still carry some uncertainty. And there is an even deeper limit to our knowledge: cosmic variance. Cosmic variance is the idea that we only have one universe to observe. We cannot run experiments. We cannot create a second universe for comparison. So there is always a limit to the precision of our statistical measurements. For example, when we measure the CMB, we observe fluctuations, slightly warmer and slightly cooler regions. And we can measure their typical size, but we only have one sky to observe. We cannot observe multiple universes to see whether those fluctuations vary. This creates a fundamental limit on accuracy. We can improve telescopes and detectors, but we cannot overcome the limit imposed by cosmic variance. It is like trying to understand Earth's climate by observing only a single year. You can measure the temperature every day with perfect precision, but you still do not know whether that year is typical or unusual compared to the long-term history. Similarly, we can measure our universe with high precision, but we do not know whether our universe is typical among all possible universes. And that leads to deeper questions. Could there be multiple universes? A multiverse? Some theories in physics, especially eternal inflation, suggest that our Big Bang may be just one of many. That inflation never truly ends, but continues in some regions, creating new bubbles of space, each with its own Big Bang. If so, our universe would be just one bubble in an endless cosmic foam of universes. And other universes might have different physical constants, different electron masses, different strengths of gravity, even different numbers of spatial dimensions. But we cannot observe these other universes. They lie beyond our cosmic horizon. Light from them can never reach us. So the idea of a multiverse, while fascinating, is not testable. It lies beyond experimental science. And that reminds us again that there are limits to what we can know. But there are other mysteries closer to home, things that may exist within our own universe, but have not yet been detected. One of the strangest is cosmic strings. Cosmic strings are not strings in string theory. They are topological defects predicted by some theories of the early universe. Imagine water freezing. If it freezes quickly and unevenly, cracks can form, lines where the crystal structure does not align perfectly. Similarly, as the universe cooled after the Big Bang, different energy fields settled into lower energy states. If this happened unevenly, cracks could form, lines where the fields do not match. Those cracks would be cosmic strings. If they exist, they would be incredibly thin, perhaps only 10 to the power of minus 30 meters across, far smaller than an atomic nucleus, but extremely massive. A 1-meter segment of a cosmic string could weigh billions of tons, and they would stretch across the universe, possibly millions or billions of light years long, or form enormous loops. Cosmic strings would have strong gravitational effects. They would bend space around them, producing gravitational lensing. If a cosmic string passed between us and a distant galaxy, we might see two identical images of that galaxy, one on each side of the string. And as cosmic strings move, vibrating or colliding, they would generate gravitational waves with distinctive signatures. Scientists have searched for evidence of cosmic strings in the CMB, in gravitational lensing, and in gravitational wave signals. So far, no confirmed detection has been made, but that does not mean they do not exist. They may be rarer than predicted, thinner or less dramatic, or they may not exist at all, which would also teach us something about the physics of the early universe. So the search continues. In every search, whether it finds something or not, teaches us something about the universe. And there are other mysteries. Dark matter, we know it is there, but we do not know what it is. Dark energy, we know it is driving the expansion of the universe, but we do not know why. Inflation, We have indirect evidence for it, but we do not know exactly how it works or what caused it. The universe before the Big Bang, if anything existed, we cannot observe. The ultimate fate of the universe, will it expand forever? Will dark energy tear it apart? Will something else happen? All of these questions remain unanswered, but that is not a failure. It is a sign of healthy science. Science advances by recognizing what we do not know, by asking questions, by searching for answers. And every answer opens new questions. Every discovery reveals deeper mysteries. There is a light that fills the entire universe, a light older than any star, older than any galaxy. It comes from a time when the universe was only 380,000 years old, just 0.003, 3% of its current age. It is the first light that could travel freely through space. And it is still traveling, still reaching us, right now. If your eyes could see microwaves, you would see it, a faint, warm, uniform glow filling the entire sky, coming from every direction at once. That is the cosmic microwave background, the CMB, and it is one of the most important sources of information we have about the early universe. Let's understand it from the beginning. In the first 380,000 years after the Big Bang, the universe was a hot plasma, charged particles, protons and electrons, moving freely, not yet combined into atoms. In this plasma, photons, particles of light, could not travel far. They constantly collided with free electrons, scattering in chaotic zigzag paths. The universe was opaque. Like a dense fog, light could not pass through. But as the universe expanded, it cooled. And at around 380,000 years, the temperature dropped to about 3,000 Kelvin, cool enough for electrons to combine with protons, forming neutral hydrogen atoms. This process is called recombination, and suddenly, photons could travel freely. No more free electrons to scatter them. The universe became transparent for the first time. Those photons, released at the moment of recombination, began traveling through space. And they have been traveling ever since. Over 13.8 billion years, they have moved through expanding space. And as space expands, their wavelengths stretch, cosmological redshift. Originally, this light had a temperature of about 3,000 Kelvin, visible light, glowing red-orange like embers. But after 13.8 billion years of expansion, it has been stretched by a factor of about 1,100. It is now microwave radiation, invisible to human eyes, with a temperature of about 2.7 Kelvin, just 2.7 degrees above absolute zero. That is the CMB. Light, from the moment the universe became transparent, now cooled and redshifted into microwaves. The CMB was discovered by accident in 1964 by Arno Penzias and Robert Wilson. They were testing a radio antenna and kept detecting a faint, persistent noise coming from all directions. They thought it was an error in the instrument. They even cleaned out pigeon droppings from the antenna. But the noise remained. Eventually, they realized they were detecting the CMB, light from the Big Bang, predicted by theory but never observed before. This discovery won the Nobel Prize and confirmed the Big Bang theory. But the real excitement came later, when scientists began measuring the CMB with high precision. The CMB is not perfectly uniform. It contains tiny fluctuations in temperature. Some regions slightly warmer, some slightly cooler. The differences are incredibly small, only a few parts in 100,000. If the average temperature is 2.725 Kelvin, the variations are about plus or minus 0.0002 Kelvin. But these tiny fluctuations are profoundly important. They are imprints of density fluctuations in the early universe. Regions that were slightly denser, warmer in the CMB, and slightly less dense, cooler. And these fluctuations are the seeds from which all structure in the universe grew. Slightly denser regions had slightly stronger gravity. Over millions of years, they pulled in more matter. They grew. Eventually, they became gas clouds, then stars, then galaxies, then clusters. So when you look at a map of the CMB, a temperature map of the universe at 380,000 years, you are looking at the blueprint for every galaxy in the universe today. You are seeing the seeds of the Milky Way, of Andromeda, of every cluster and supercluster. Satellites like COBE, 1989, WMAP, 2001, and Planck, 2009, have mapped the CMB with increasing precision, revealing the pattern of these fluctuations in extraordinary detail. From those maps, scientists can extract an enormous amount of information about the universe. They can measure the age of the universe, 13.8 billion years. They can measure its composition, about 5% ordinary matter, 27% dark matter, and 68% dark energy. They can measure the geometry of space, flat, within measurement limits. They can measure the early expansion rate and test inflation theory, all from tiny fluctuations in the CMB. But the CMB is not just about temperature. It also has polarization. Light is an electromagnetic wave, and waves can oscillate in different directions. Unpolarized light oscillates randomly. Polarized light oscillates preferentially in certain directions, and the CMB has a small but measurable polarization. This polarization was created when photons were released at recombination. The way they last scattered, their directions, the structure of the surrounding plasma affected their polarization. There are two types of polarization patterns, E modes and B modes. E modes are common. They are generated by ordinary density fluctuations, the same ones that produce temperature variations. B modes are rarer and more interesting. They can be produced by two effects: gravitational lensing, the bending of light by large-scale structure, and primordial gravitational waves. Primordial gravitational waves, if they exist, would have been generated during inflation, in the first fraction of a second after the Big Bang. They would be ripples in space-time itself, generated as the universe expanded at an extraordinary rate during inflation, and those ripples would leave an imprint in the CMB, a distinctive pattern of B-mode polarization. Detecting primordial B modes would be one of the greatest discoveries in physics, directly confirming inflation and providing a window into the universe at around 10 to the power of minus 35 seconds after the Big Bang. In 2014, the BICEP-2 experiment announced that they had detected primordial B modes, but later analysis showed that the signal was likely caused by dust within our own galaxy, not the CMB. So the search continues. New experiments with higher sensitivity are looking for weaker primordial B modes, trying to separate them from dust and other sources of noise. If they are found, we will have direct evidence of inflation and of gravitational waves from the very first moments of the universe. And the CMB also reveals something else: the history of cosmological redshift. Light from the CMB has traveled through 13.8 billion years of expanding space. At every moment, space stretched slightly, lengthening its wavelength. Over billions of years, the effect accumulated. Light that was once at 3000 Kelvin is now at 2.7 Kelvin, redshifted by a factor of about 1,100. This tells us that the universe has expanded roughly 1,100 times since recombination, and redshift does not apply only to the CMB. It applies to all light from distant objects. A galaxy 1 billion light-years away has a small redshift. Its light is only slightly stretched. A galaxy 10 billion light-years away has a larger redshift. Its light is stretched much more. The most distant galaxies we observe, from when the universe was only a few 100 million years old, have extremely high redshift. Their original ultraviolet light has been stretched into the infrared, and redshift is not caused by galaxies moving through space. It is caused by space itself expanding, carrying galaxies along and stretching light as it travels. This is a subtle concept, but here is one way to think about it. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, the dots move farther apart, but the dots are not moving across the surface. The surface itself is expanding, carrying the dots with it. Similarly, galaxies are not flying through space. They do have small motions, but those are minor compared to expansion. Space itself is expanding, carrying galaxies along. And as light travels through expanding space, its wavelength stretches redshift. So the CMB, with its tiny fluctuations, its polarization, its enormous redshift, is a treasure trove of information about the early universe. It tells us what the universe looked like at 380,000 years. It tells us the seeds of structure. It tells us the composition, age, and geometry of the universe. And perhaps, if primordial B modes are detected, it will tell us about inflation and the very first moments after the Big Bang. The CMB is a photograph of the young universe, the oldest image we can possibly have, taken when the universe was just 380,000 years old. And that image is still here, covering the sky, waiting to be read. We have journeyed across 13.8 billion years from the Big Bang to today, from pure energy to matter, to stars, to galaxies, to you. And here is the final wonder I want you to remember as you drift into sleep. You are made of stardust. Every atom of carbon, nitrogen, and oxygen in your body was forged in the core of a star that lived and died billions of years ago. You are not separate from the universe. You are the universe, a part of it experiencing itself. The stars are still shining. The universe is still expanding. And you, in your quiet sleep, are part of that vast journey. Sleep well, held gently in the vast, calm, eternal universe.